Let's talk about the direct comparison test. So in this test, we are still trying to answer that same question that we've been answering, which is, here's a series, does it converge or diverge? The direct comparison test will be one of many, many tests we have to attempt to answer that question. All right, so what I have here is kind of my interpretation of this test. You should have like the official book version written down in your notes, and this is just sort of slightly different from it. Okay, so in the direct comparison test, normally when it's useful is when the series that you're given is similar to one that you know. And by know, I mean like you know something about it just by looking at it. You know whether it converges or diverges. And for us, that means it's a P series, right? That converges if P is greater than 1. Or it's a geometric series which converges if the absolute value of R is less than 1. All right, so you say, okay, my series looks similar to this other one. So there's like this second thing to compare to. And the theorem, or the test rather, that's what we're going to call the series of BKs. So this is the one that we're actually trying to figure out. This is one that's similar and we know the answer. So we kind of come up with this. The only requirements for this test to be okay to use is that the terms of both series involved, so the one you start with and then the one you pick, the terms of both of those series should be positive, right? So you shouldn't have terms hitting 0, they shouldn't be going negative. But usually that's fairly easy to set this up. All right, so there's 2 scenarios that can come out of this test to conclude either converge or diverge, depending on what's happening. And it's all about comparing the terms of the series you started with the terms of the series you kind of came up with as your first step. So if your terms are less than or equal to the terms of the other, and the other one you know is convergent, then that's enough to say that yours is also convergent. On the flip side, if your terms are greater than or equal to those other terms, and that other series is divergent because of what you know, then your series is also divergent. So one thing that freaks people out in this test is this like extra phrase here, for all k greater than or equal to some number. It's in both sentences here. In the textbook, they say this for all n greater than or equal to capital N. It seems kind of unhelpful. So what they're trying to say with this phrase is like, this should always be true, right? For every single k, you should always be less than or always greater than to make this conclusion. But technically, you can loosen that requirement a little bit and say, okay, it's fine if the first few don't have this relationship, as long as after a certain point, this is always true, right? So for k, as long as the terms are greater than 10 or whatever, like this is true. So technically, it's like an eventually thing here. It's not something we usually have to worry about. It just kind of broadens the capabilities of the test. Okay, so let's summarize this just a tiny bit, just to keep track of all the information that we have. Okay, so essentially, if you can show your terms are less than or equal to the terms of a convergent series, then you've proven that you're convergent. If you can show that your terms are greater than or equal to the terms of a divergent series, then you've proven that your series is divergent. Okay, so that also gives us kind of 2 other cases that are technically inconclusive from the direct comparison test. So if you can show you're less than or equal to some other series terms, but that series is divergent, that doesn't get you anywhere, right? So if it's less than or equal to, you have to be comparing to something convergent for it to be useful. But less than or equal to divergent just isn't a thing. It doesn't help you conclude anything. Similarly, showing that your terms are greater than or equal to the terms of a convergent series is not enough information to kind of conclude anything. So if you can only show you're greater than or equal to the terms, then it would have to be the terms of a divergent series for it to actually get you to an answer. Okay, so when you're applying this test, the first thing you're going to do is choose a series to compare it to. And again, it should be either a P series or geometric series that you know whether it converges or diverges, because that's step 2. So you choose a second series, which we'll get practice with. Determine if that thing is convergent or divergent. If it's convergent, you're going to attempt to show that your terms are less than or equal to those terms. If that's possible, you say, okay, it's convergent, I'm done. If that's not possible, you just say, this is inconclusive, I gotta try something else. If that series is divergent, you'll attempt to show that your terms are greater than or equal to those terms. If they are, you say divergent. If they aren't, again, inconclusive. And you have to try something else, either a different comparison or just a different test altogether. All right, so let's see this test in action. Move on to another piece of paper here. All right. So let's say we have k equals 1 to infinity, 1 over k squared plus 1. This is also a great candidate for the integral test, but we're going to use this for the direct comparison test instead. All right, so my first step is supposed to be to choose a series to compare it to. And the more you practice these, the more you kind of get some instincts, but generally what's going to help you decide is ignore any like plus one minus, so plus a number minus a number. Without that plus one, this is 1 over k squared, and that's a p series, right? So I'm going to choose to try to compare this to 1 over k squared, and we'll see if it works out or not. So I'm going to compare it to 1 over k squared. And at some point, we technically should be very, very responsible. If we come back to the statement of the test here, we have this requirement that all the terms are positive, which, is not hard to meet, but we should double check that we're not violating that. This is definitely always a positive number. There's no way this is going to go negative. Same thing here. This isn't going to go negative, so we're good. Okay, so step 2 is determine if your new series that you just came up with is convergent or divergent. This is a p series where p equals 2, so this is convergent. And if we're being really thorough, we would say it's convergent by the p-test. Okay, so we are hoping that we can show that our terms are less than or equal to those terms, but if we can't show it, then we're inconclusive. So it turns out that for every k, 1 over k squared plus 1 is less than or equal to 1 over k squared. And it doesn't even seem like I really did work, right? Like I just kind of wrote what I needed. But the reason this is true is that the difference between the two is this plus 1 right here, right? So this fraction right here has a bigger denominator than the other one. A bigger denominator and everything else the same means a smaller fraction. Bigger denominator is a smaller fraction. So anytime you add a little bit on the bottom, you've made your fraction smaller. So this statement really is true in a single step. On the flip side, when you need it, a smaller denominator would give you a larger fraction for the same reason. All right, so for every k, this is less than that, and this series is convergent. So the series that I started with is convergent. And if we're being really thorough, we would say convergent by the direct comparison test. Oops, there we go. It's convergent by the direct comparison test. Notice how one tiny change to this series and the direct comparison test would actually not be helpful. So let's say we have the same series. I'm going to start it at 2 just so we don't have a domain issue here. But instead of 1 over k squared plus 1, I'm going to say 1 over k squared minus 1. So I bumped it to 2 just so that we don't have dividing by 0 in the first term. But otherwise, it's really, really similar, right? Just a minus sign. If I tried to do the direct comparison test on this, I would take the same couple of steps here, right? I'd say, okay, without the minus 1, it looks like 1 over k squared. So the only obvious thing to compare to is 1 over k squared, which of course is convergent by the p-test, just like it was before. But now all we can say is that 1 over k squared minus 1 is greater than or equal to 1 over k squared. Because it's a smaller denominator, we've subtracted from the denominator. The smaller denominator is always going to give you a bigger fraction. So this one is larger than this one. So what we have is one of those inconclusive cases from before. If we come back to these notes here, what we have shown is that we're greater than or equal to something convergent. So we can tell it's really similar to something convergent, but we can't quite say that it definitely converges. So the direct comparison test, at least for this series in this scenario, is inconclusive. So what you would do with a problem like this kind of depends on the instructions you're given. So if you had to use the direct comparison test, right, the instructions tell you to use this test with this series, the best that you could do is just say, you know, inconclusive because they match up this way. If it was just, here's a series converge or diverge, once you get here, you say, okay, I've got to try something else, right? You know, maybe try to find something else to compare to, or just move on and try a different test to see if it works a little bit better. So if you want to see more examples of using this test, take a peek in the textbook in section 8.3, and then otherwise we'll do a bunch together in class.